Hello, everyone. Thank you so much for coming to our talk. This is ML AI 225, Machine Learning with TensorFlow and PyTorch on Apache Hadoop using Cloud Dataproc. So I'm Brad Miro. I'm a developer programs engineer on Google Cloud.
Hi, I'm Gonzalo Gasca. I'm also a developer programs engineer in cloud.
So this is Thursday morning. You've probably seen this slide 100 times already, but we will be having a Dory accompanying this talk. So if at any point during the talk you have any questions, feel free to just go into the Dory on the app, ask the questions, and then we'll be going through them at the end and getting you the information that you're looking for. So what we're going to discuss today, we will start by discussing machine learning on Apache Hadoop generally. We'll then discuss Cloud Dataproc, which is Google Cloud Platform's managed Apache Hadoop and Apache Spark service. We'll then discuss distributed machine learning, some strategies for doing that, how you can actually solve this problem currently. And then we'll show you a demo of running TensorFlow and PyTorch on Cloud Dataproc. So let's just dive right into it. But before we do that, I just want to survey the room very briefly. Who here uses Apache Hadoop on a regular basis? Just a quick show of hands. Awesome. What about who writes machine learning algorithms on a regular basis? Just another quick show of hands. OK, a few more hands. And lastly, who uses TensorFlow and or PyTorch on a regular basis? Awesome. OK, cool. So we'll just start with a bit of a survey of what the Hadoop and machine learning ecosystems look like. Starting on the left, you have, in the Hadoop ecosystem, you have your Apache Hive, your Apache Pig, your Presto. Those are for, of course, querying Hadoop for your data. And then you have Apache Spark for running ETL jobs and loading your data into memory. And of course, the rich ecosystem that comes with Apache Spark specifically. On the right side, on the machine learning side of the Venn diagram, you have your packages such as XGBoost and scikit-learn. And then, of course, in the deep learning circle, deep learning being a subset of machine learning, we have TensorFlow, PyTorch, and Keras. If we look at the intersection of the two sides of the Venn diagram, you'll notice that we have Spark MLlib, which is very similar to scikit-learn, for those of you who may be familiar with that, for running machine learning models on Hadoop. But noticeably, there's nothing in this section here for doing TensorFlow or PyTorch. So let's discuss how to get there. But why should you care, of course? So you may already have an Apache Hadoop cluster, and you may have pre-existing investments there, and you want to, instead of spinning up new infrastructure, you may just want to run your jobs there and see what some potential models may look like. You also may have existing workflows for loading data into and out of Hadoop. And of course, if you have all of your machine learning processing running on Apache Hadoop, you don't have to worry about the workflows changing, and then you're able to leverage them that way. And then, of course, being Apache Hadoop, you are in the world of distributed processing. So, of course, you can leverage that here as well. So TensorFlow and PyTorch, we're just going to go over these briefly, what they are, as they're mentioned in the title, of course, and we're going to talk about them today. So TensorFlow being an open source machine learning framework that is developed by Google. It has access to distributed machine learning, so it is built into the framework itself, and there's ways that you can do that. It has a very rich ecosystem of packages such as TensorFlow Extended for building end-to-end machine learning pipelines, as well as TensorBoard, which is a nice UI for actually seeing your models as it's training, and you can set the metrics on there that you want to see, including accuracy or loss. TensorFlow also utilizes Keras as its high-level API. For those of you who have used Keras before, you know how user-friendly it is and how, in my opinion, fun it is to use. So of course, that is built right into TensorFlow. And TensorFlow is also perfectly suited for both production and research. So there's, for all of your needs, you can utilize TensorFlow. I just want to do a quick shout out that TensorFlow 2.0 alpha was just released. So if you're interested in learning more about that, check out tensorflow.org, and you can get started playing around with the 2.0 version. And then, of course, we're going to talk about PyTorch too. PyTorch is an open source machine learning framework that was developed by Facebook. PyTorch also supports distributed machine learning natively, so you have access to run those distributed jobs using PyTorch. PyTorch has built-in model layers, so there's classes for things such as an RNN layer or a convolutional neural network layer. So you have access to those just right out of the box. And then, of course, PyTorch is also perfectly suited for production and or research, depending on your needs. So now that we've discussed machine learning on Apache Hadoop, let's discuss Apache Hadoop as it pertains to Google Cloud Platform. And so our solution to a managed Apache Hadoop service is Cloud Dataproc. And so what is Cloud Dataproc? It contains managed clusters for Apache Hadoop and Apache Spark. Cloud Dataproc allows you to deploy clusters in 90 seconds or less on average for very quick uptimes. When you're using Cloud Dataproc, you only pay for the time that your queries are running, also known as compute time. It's perfectly suited to be configurable with open source solutions. So of course, we have Apache Hadoop, we have Apache Spark, we have Apache Pig, Apache Hive, as well as what we call optional components, which are some of your favorite open source data science libraries that you can include with your cluster when you spin it up. So that includes things such as Anaconda, Jupyter, Zeppelin, Presto, and there's a whole long list of them that you can find on our website. And Cloud Dataproc has seamless integration with a lot of GCP services, including BigQuery and Google Cloud Storage Connector. Cloud Composer also has a Cloud Dataproc operator, which makes spinning your cluster up and down using Cloud Composer super easy to do. And then Cloud Dataproc also has the Autoscaling feature that is currently in beta. And Autoscaling is a really nice feature. We're going to talk a little bit more about it later in the session. But the idea behind it is that as your loads, or as the pressure on your cluster increases or decreases, Cloud Dataproc can actually add or remove workers without you having to manually go in and add them yourself. You can do that, of course, but this feature allows you to not have to do that. And so we'll just discuss a little bit more about the architecture behind Dataproc. This will be fairly high level, but we'll just give you a little bit more of an insight. So starting on the left here, you can see that we have your networking and your IAM layers like you would for any other GCP service in our stack. Next, you have the Cloud Dataproc API. And so this is really awesome for actually interfacing with your cluster. You have the ability to interact with the cluster also via the UI, but using the Cloud Console commands, you can interact with your cluster. You also have access to the Jobs API, which allows you to preset what type of job you're submitting. So for instance, if you're submitting, let's say, a PySpark job to Cloud Dataproc, you can set that when you submit the command, and then this way, Cloud Dataproc will pre-configure the runtime environment for you. And then you also have access to your Hadoop and Spark operations via the Dataproc API. So you have access to all of those tools through the API. And then, of course, within the cluster itself, so you have your Cloud Dataproc open source image. And so as I mentioned earlier, that can include your Apache Spark, your Apache Hadoop, Apache Hive, Apache Pig. And then there's the optional components that I was mentioning as well. So here we have Jupyter, Zeppelin, and Presto mentioned, but there's a whole list of them. As I mentioned earlier, you can do Anaconda, you can do RStudio, there's a whole bunch of them. And then, of course, being a Hadoop cluster, of course, you can write out to either HDFS or to Google Cloud Storage. So now that we've discussed machine learning on Apache Hadoop and Google Cloud Platform's solution to having an Apache Hadoop service, we're going to talk about distributed machine learning right now. And I think Gonzalo has something to say about it.
Perfect. Thanks, Brett. So what is distributed machine learning and why it's important in the context of Hadoop? I mean, if you're a machine learning engineer, a data scientist, or you've been experimenting with deep learning models, you probably know like when you are training large machine learning models, they take a very long time. So some models may take like a couple of hours. Some models take days, and there are like very large models that may take even weeks to complete training. So the first application for distributed machine learning is try to reduce this training time. Another application for distributed machine learning will be try to run experiments in parallel. So for example, if you are doing hyperparameter searching, you can run multiple models simultaneously, so you can save some time. So let's take a look at how this journey looks like. So normally when you are experimenting with your deep learning models, you can use your local computer or a virtual machine in the cloud, and you start with a multi-core CPU. That might be OK for like very small training models. But if you really want to take advantage and reduce the training time, you can use accelerators. An accelerator could be a TPU, a GPU, or an FPGA. For this talk, I'm only going to be referring to accelerators as GPUs. So what do? You install the drivers, you attach your device, and if you're using like frameworks like TensorFlow or PyTorch, you need like very little or no code modification to start training your models. If you can attach one GPU, I mean, why not to attach more GPUs? Again, you attach more GPUs, you start doing your training, And if you're using a framework like TensorFlow, there's something new in TensorFlow which is called distribution strategies. So with distribution strategies, the goal of the TensorFlow API is like, don't care too much about the underlying infrastructure. So you just define what is your underlying architecture. So for example, if you're running a single node, you might just define like, oh, OK, I have 2 GPUs. So you can continue adding GPUs into your single node, but at some point, you're going to hit some hardware limitations. And from an architectural perspective, you need to, instead of scaling up, you want to scale horizontally. Right? So the next obvious step is going a multi-node, multiple GPUs. While multiple node and multiple GPUs might help you reduce your training time, in reality, you need to consider other factors. For example, how's the communication between the devices and like network overhead between those multiple nodes, right? So when we talk about distributed machine learning, there are like 2 main paradigms that we always need to talk about. So the first paradigm is called data parallelism. So with data parallelism, you normally have your neural network or your model, and you store it locally, and then you start training your model with different slices of data. So this could be synchronous or asynchronous. If it's asynchronous, which is like the traditional way of doing TensorFlow, you normally train your model different slices of data, and the workers might be doing the heavy lifting. For example, they will be computing all the gradients, and your parameter server or like another server might be just doing the averaging of those gradients. That would be like the asynchronous way. And there are like new techniques, like new distribution strategies. For example, Miro strategy, which actually is called synchronous, where like all the devices compute the gradients locally, and they communicate those directly or indirectly to others. They will be updating the model only when it's required. But sometimes your model is quite large that you actually cannot fit it into one device. So if you think of like a neural network, you might need to split these different layers into multiple devices. So TensorFlow allows you to execute different parts of the graph in different devices. This is called model parallelism. So an example of these models would be like wide and deep neural networks. And one example is the Google neural machine translation model. That's like a very large model. So this slide is taken from the TensorFlow webpage. This is a training model that the TensorFlow team did. So basically what they did was they collected 4 different models, which are very popular for benchmarking: Inception V3, BGG16, ResNet 50, and 152. And they trained them with different GPUs, 1, 2, 4, and 8. So what they actually found is like the more GPUs that we actually add, the faster we can process those images. So you can see there's a linear growth based on the number of GPUs that we add. And the faster we are actually able to process those images, the faster the training is actually happening. But I mean, what happens when you go from research or experimentation to production? There's more than training, right? So you normally have a pipeline. And we have a very, I'm going to go through like a very simplified, like probably oversimplified machine learning pipeline. And you could start with data preparation. So think about like feature engineering or your regular ETL process, where you are collecting your data, you are selecting which features you need. And normally in this case, you don't need a GPU. Probably you are fine with a CPU cluster. If you think of like the Apache ecosystem, you will be using Apache Spark on this one. Once you collect your data and it's ready to be trained, you have your trained data now, you move to a different stage, which is like the training data. So we just agree that using accelerators is a good option, and you have access to those devices. In reality, like if you work with different departments or you are running different experiments in your company, you probably need to be considerate about how you use these devices, right? Like when you allocate a GPU, when you allocate other accelerator, you need to make sure that you need a resource manager. It's not like I'm just going to be configuring my TensorFlow webpage and my TensorFlow work, and it's just going to be working. So once you move from training, you go to the serving phase, where you can have both of CPU and GPUs. So if you think of like serving, you will use like Kubernetes, maybe some Docker containers running TensorFlow serving, and you will be fine maybe with CPU. But if you really want to increase the speed for your inference, you may want to add like GPUs. A good example of like a GPU that is designed only for inference would be like the Tesla T4 from NVIDIA. So we agree that when you use resources, you need a resource manager. And there's already like applications that solve this problem. Like, think about Yarn, think about Mesos or Kubernetes. But how do you configure actually TensorFlow to have access to these devices, right? In the classical way for configuring TensorFlow, you normally define your cluster, and you define the IP addresses and ports which are going to be running your TensorFlow code. You might define your workers, your parameter servers, then you stop and you start your servers based on your job. But this is something like data scientists don't really want to do, or this is like very focused on dev operations. There's something called tfconfig, which is an environmental variable that is designed to address this problem. So a lot of resource manager, like Kubernetes supports this environmental variable. So basically, you define a cluster specification, which you're only going to be reading, and then from there, you can execute your code. So we're going to go through some of the list of products that actually already address this problem, like meaning resource allocation and running distributed machine learning workflows. Who is familiar with some of these products, like Qflow, AI Platform, Horobot, TensorFlow and Spark, or Spark Deep Learning? Anybody has used any of those? Yeah, cool. So one of the things that we care in the context of this talk is that it's supported on Yarn, right? It runs on Hadoop. So the first product is Qflow. So it's based on a Kubernetes environment. So this might not be a good option. The second one is AI Platform. It's previously known as Cloud Machine Learning Engine. We just changed the name. And this is great for model training, inference, and model versioning. But it's a hosted solution by Google. So you really don't care about infrastructure. So we just bring your model, and we handle the infrastructure for you. The other one is Horobot. It's more like a library. So Horobot is a library by Uber. So Horobot, the problem that was trying to solve is running distributed machine learning on top of TensorFlow to be able to speed up the training time. And it doesn't really run on Hadoop. It's more like a helper. And then we have two products, TensorFlow and Spark from Yahoo, which was one of the best of the first solutions for this to trying to address this problem. So TensorFlow and Spark runs on two different layers: the Spark layer, and then the TensorFlow layer, the Spark layer, and the Yarn layer. From this, you rely on the Spark to do the resource allocation, and then you need to pass that request to Yarn. So you need like very little code modification, and it works great from some workflows. The other one is Spark Deep Learning from Databricks. So it follows the same paradigm. And it integrates very good with the MLflow ecosystem from Databricks. But one of the things that we actually care is GPU support. So when we think of GPU support in Hadoop, if we're using, there's something that we need to mention. So Hadoop version 3.1 is the version that in reality supports GPU allocation. This means like when you are attaching a GPU to your devices, Resource Manager in Hadoop is aware that you have a GPU connected. Before Hadoop 3.1, there's another workaround which is using node labels. So basically, you tag your servers that have a GPU. So when you run your jobs, you basically route that job to the servers that have a GPU already. But it's not like native support for GPU. One of the problems with this is that when you use TensorFlow and Spark or Spark Deep Learning, is that you have a layer on top, which is Spark. So Spark also requires to be able to be aware of the GPUs. And there's already some work in the Spark community. I think Spark 3.0 is going to be supporting this, but there's still a Jira open for this issue. So that's why it's important to, if we really want to take advantage of the GPU, have native Yarn support. So then it comes TonY. What is TonY? TonY is a project which stands for TensorFlow and Yarn. Also, it also supports PyTorch. So the main functionality for TonY is orchestrate distributed TensorFlow or PyTorch jobs in Yarn but it also supports single jobs. So you can bring your single node job and execute it on Hadoop. It was developed by LinkedIn, and it was open source back last summer. So what are the important things about TonY? So TonY is going to be supporting first-class jobs from running on Hadoop. This means like when you run a TensorFlow job or PyTorch job, it's going to be the same as you were running on a Spark job. It's just run on the same level. If you're already invested in Hadoop and all your infrastructure, but you want to start experimenting with deep learning, we want you to use to minify your infrastructure very little, so your data scientists and machine learning engineers can start to using the product. So TonY allows you to have a client, and we're going to go more into details. You're going to have a client that you're going to be using to execute your jobs. And one of the features from TonY is that you can request resources in a very fine-grained manner. This means like if you have a TensorFlow job or PyTorch, you can request how much memory, how many cores are you going to be using, and how many GPUs. And jobs require very or little parameters. So normally when you execute a Python script, you have a virtual environment with all your libraries, and you have your Python files, right? So what other thing we need? You need a configuration file. So as little as 3 options, you can actually execute a TonY job, although there are like other possibilities. And if you're running long training jobs, you want to make sure that those jobs actually complete successfully. So when you launch a TonY job, you need to be able to verify that all your workers are executing correctly, and if some of your containers actually fail, you need to be able to restart it. So let's take a look at the TonY architecture. The first thing that when you want to run a TensorFlow job or PyTorch job that you need to bring is your code, right? So you bring your code, and the second thing is you need to bring your virtual environment. So the virtual environment is going to be in a zip format or like compressed. And finally, your configuration, which is the resources that you actually need. So this configuration is an XML file that you can define where you, when you have like CPU, how much memory you require for each of the workers, and how many GPUs you need. So those 3 things are the first part of running a job. Then you need the TonY client. TonY client is a jar file that is compiled using Gradle. So TonY is built on Java. So when you launch TonY, when you're going to be launching a TonY job, you execute the job, and it's going to contact Yahoo Yarn, Hadoop Yarn, and it's going to spin off a container. So this is the application master container. So application master container is going to see what you configure and negotiate the resources with Yarn. So for example, if you negotiate 3 workers, it's going to try to allocate resources for those 3 workers. That's the second element of TonY. Then you have your task executors. So task executors is actually your machine learning code that is executing, and those are based on the resources that you requested. So those are Yarn containers. So task executors is going to be your machine learning code that is actually executing. So we have talked a lot about different topics, but do you think it's time for a demo?
I think it is. I think we should show our audience a little bit about how to run TensorFlow on Google Cloud Platform.
Okay.
So I know we were discussing before this talk that you had actually set up a Cloud Dataproc cluster. Do you mind telling us how you may have done that?
Sure. Creating a Dataproc cluster is very simple. So the first thing that you need to use is you can use the gcloud command, or you can use the UI. If you want to use the gcloud command, you just need to define your cluster name and the number of workers. This will be your node managers in Hadoop. Then we can take advantage of a feature called initialization action, which are shell scripts that are going to be executed during cluster creation time. In this case, we have 2. The TonY shell script and the GPU drivers. The TonY shell script, what it's going to do is going to clone the code from the GitHub repo, and it's going to build the jar file for TonY. In the official shell script, we also provide 2 samples, one with TensorFlow and one with PyTorch code that you can actually use. In the second shell script, what we do is because we want to use GPUs, we need to install the drivers, and we need to set up a service, a stack driver service that is going to be monitoring the GPU utilization. In this case, we're going to be using 2 GPUs. So for each of the workers, we're going to be attaching a Tesla V100 GPU. And because we want to run many jobs, we want to enable auto-scaling policy.
Awesome. Well, thank you for telling us that. I think we should now run some jobs.
OK.
Right?
Sweet.
So, floor is yours. Can we switch to the demo, please? Thank you.
Perfect. So we created a cluster in advance. This has 2 workers. Let's go to the instances. You can see here there's the master node, and then the 2 workers with each of those has a GPU. So let's run some jobs. I'm going to be running one TensorFlow job to start.
Wait, you're only going to run one? Hold on, we have autoscaling enabled. We can do more
Maybe
than
2.
one. How about 10?
OK.
And let's do a PyTorch job also for good measure.
OK.
Cool.
Perfect. So I created a script that is going to be launching those TensorFlow jobs. And let's take a look at this script. So I'm using the gcloud command to run the TensorFlow code. So in this case, we're submitting a Hadoop job in the cluster that we just created. The TonY client is just a jar file. So we define the jar file here. And because it's a Java file, we just need to define the class. One feature for TonY is also not only allows you to run Python code, but you can also run notebooks, like Zeppelin notebooks, or you can even run Docker containers. The only requirement is that your Hadoop infrastructure is ready for Docker. So in this case, we're actually running Python code. So when we were talking about how TonY is minimalistic in terms of executing code, one of the things that, as you can see, try to emulate is if you're a data scientist, you normally run a Python command like this, right? You have a virtual environment, you live in a source directory, and then you run Python and your Python file. And because this is machine learning code, you should be able to pass some parameters. So this is exactly what actually TonY requires. So here you pass the virtual environment. This is your zip virtual environment. You pass the Python executable, and then your script. In case you have more files, by defining the source directory, you should be able to get all those dependencies.
Gonzalo, what is that MNIST distributed Py job? What is that actually going to be doing?
So in this case, what we're going to be doing is we're going to run the Hello World for machine learning, but distributed, where we're going to be using the MNIST dataset. So it's a convolutional network for digit detection.
OK, cool.
And finally, we have the configuration file. Let me go back here. Oops. So this is how your TonY configuration file looks like. In this case, we're going to be spinning off 2 workers. This is the requirements for memory. We're going to be using 1 parameter server. This is the requirement for our parameter server, and 1 GPU. So let's take a look how this looks in Yarn.
Wait a minute. I asked for a PyTorch job, and I haven't seen any PyTorch yet.
OK.
So let's get some PyTorch in here.
So in order to run this PyTorch job, we're going to be using the Dataproc API. So Dataproc allows you to run, to submit Python code, very similar as you do the gcloud command, but from the API directly. So what I'm doing is just importing the Dataproc API. I'm defining my project. So in this case, you can see my project ID, my region, and this is the TonY client. So it's a jar file. So we talk about like how Dataproc by default has the GCS connector. So you can actually, without any configuration, have access to your gcloud bucket. So this is like using the latest TonY version, which is 0.3.1. We define the class. This is just a helper function. And this is how it normally looks in the gcloud command that we just launched. But we're going to do it from the client. So you define your job controller, your arguments. You create your Hadoop job. And then you're going to define which cluster you're going to send this job. And now we just send the job. Let's take a look at Dataproc for all these jobs. Let me go to the cluster so it's actually easier. So here are our 10 jobs, and this is just the PyTorch job that we just created. And you can see that one job already completed. We can use the monitoring tab, and there's a lot of memory being used that is actually pending. Do you think autoscaling is going to work?
Absolutely. Can we just get the slide back, please? So let's just talk about autoscaling really quickly and how you can enable that on the cluster. So Gonzalo was showing you before how here we have the autoscaling policy that we've called autoscale TonY. And what that actually looks like is it's just a YAML file that gets uploaded to Google Cloud. Here you can see that there's only two top-level components. We have the worker config and the basic algorithm. So we'll just discuss what those are. We'll start with the worker config. You'll see here that we have two parameters set. We have the min instances and the max instances, respectively set to 2 and 10. What this means is that as autoscaling is adding and removing workers to the cluster, it will always make sure that the total number of workers is within these two numbers inclusively. So this will never have less than 2 workers and never more than 10. And how does it actually figure out how many workers it should add? So it uses the basic algorithm for that. And here we've set the time to check to be 2 minutes, as we've denoted by the cooldown period. So every 2 minutes, it'll look at the available memory that's the available memory and the pending memory, and then it'll calculate how many workers it should add. And then once it comes up with that number, it will then multiply it by either the scale up or the scale down factor, depending on how many workers it thinks it should add and remove. And so what this number does is it gives you some more fine-grained control as to how quickly you may want the cluster to scale up or scale down. In this case, we've set these both to 1.0, which means that the cluster will attempt to have as near perfect memory utilization as possible. But in the event that you don't care about that, and if there's a spike in your pending memory, you don't necessarily need to have a bunch of clusters added, you can scale this number down to, let's say, 0.5 or 0.1, just completely dependent on whatever your use case is. So you have the option there. And then last but not least, we have the graceful decommission timeout. And what this value does is if your cluster determines that it should take down some of the workers, it'll actually set, in this case, a 15-minute lag to it. So that in case there's any jobs that are currently running, you wouldn't want the cluster to just take the workers down and have those jobs disappear on you. So just a small anecdote, Gonzalo and I were recently working on a project where we were using the autoscaling feature, and we had that happen to us where the data was simply, the jobs were just failing, and we never configured this. So it was just, or I believe we had set this to 0 minutes, and then the jobs were just failing. So we added this, and of course that perfectly solved our problem. So that's autoscaling. Let's see, maybe, do we have any more workers? We started with 2. Hopefully there's more than 2.
Let's take a look. Can we go back to the demo? OK, perfect. So let me maximize this. So this is the Yarn UI. You can see that the scheduler was very busy, and some of the jobs still running, and others are still waiting to be to get resources.
Can I see that PyTorch job? Good.
Yeah. And this is when we were saying like the application type TonY is a native of Yarn. So each of these jobs requires like 12 gigabits of RAM, 2 workers, 4 gigabits each, plus the parameter server 2, plus the application container, which is another 2. That's 12 total. So you can also monitor the utilization here in Dataproc, but looks like something is happening. Let's take a look. You can see here how the cluster is being scaling up, which is very good.
I see there's 3 workers. That's great.
Yep. And you can see here this as well.
Perfect.
But let's see how the jobs are doing. Good. So what I'm going to do is just make sure like my jobs are actually completed correctly. So you can pick any of the jobs and see the configuration. And these are the exact parameters that we pass when we create the job. And we created one job identifier just for the sake of having an ID. And you can see here all our task parameters. So we are training the model with 750 steps. So I'm going to be launching TensorBoard to see that. This is just a script that launches TensorBoard locally. But the data, as you guys saw in in the training job. Let me go back here. The data actually lives in your G Cloud storage bucket. So, and we didn't need to configure anything, just out of the box. OK, so let's see if TensorBoard is running. Oh, good.
That.
So this was trained for 750 steps. And as you can see, the more steps that are actually executing, the accuracy keeps increasing. And the cross-entropy loss, it's reducing as well. This is a convolutional network. So you can see here all the graph and the nodes that are connected.
I think something cool to point out here is that using TonY on Apache Hadoop, you have access to the full suite of TensorBoard features, so as Gonzalo was showing you. So I think that that's a really nice feature to have, TensorBoard being as useful as it is and as helpful as it is for training your models. And it looks like our jobs are doing pretty well.
Yep.
Cool. So I think in the interest of time, we'll just wrap up. But you'll see that we have 5 of them finishing. And if we were to give this more time, of course, these will continue to run. If we can just go back to the slides, please. Awesome. So we'll just close out and just quickly recap what we discussed today and what we showed you. So we started off by discussing machine learning on Apache Hadoop and what that looks like, what the current landscape for that is. We then discussed and introduced Cloud Dataproc to you as Google Cloud Platforms manage Apache Hadoop and Apache Spark Service. We then discussed distributed machine learning and some of the options and strategies for doing that. And then, of course, we introduced TonY to you and showed you a demo of how you can get started using TonY. And we used Cloud Dataproc as our means to show you that. So if you're interested in learning more about this, here's the link for the actual TonY repo itself. It's github.com/LinkedIn/TonY, TONY. Also, if you have any questions, feel free to add your questions to Stack Overflow under the TonY tag, and we'll be happy to answer you. And then for the code that we showed today, we're actually going to be sharing that over Twitter in the next couple of days. So feel free to follow us on Twitter, Gonzalo at GOGASCA, and myself at BRADMIRO, Brad Miro. And yeah, so thank you everyone for coming. Just a quick shout out to we want to just thank the Cloud Dataproc team, the LinkedIn team, as well as the producers in the room, and also all of our friends who were super helpful in helping us out with this presentation.